All right, welcome everybody. This is Fred Schankelberg, and today we're going to talk about graphics. And I'm going to go into just a couple of different graphics and types of charts or plots that we could use. In the past, I've done um, uh, various presentations on mean cumulative function, on Weibull analysis, and a few others. And I think we're going to circle back to those. Those topics were a few years ago. Um, but get into more details of what makes a good specific types of graphics. And today I want to cover a couple of those. And as you know, in an hour, it's not near enough time for covering all the different ways we can present data and make a difference with it, because it includes everything from statistical process control charts like X bar and S charts, for example, which can really speak to the stability of our process that affects our reliability performance, or field data analysis using cumulative distribution functions or mean cumulative functions. And that's just scratching the surface. And so I want to cover some of the basics of and key elements that makes an effective graphic. And of course, I'm going to talk about reliability stuff, but it's more generic than that. It really applies to any graphic or any chart of data that you're using. Now, what we're really going after here is that we've got data. I remember walking into one factory in Central California that they had terabytes of data on a monthly basis. They had sensors all over their equipment and catching every single anomaly and triggers for getting the line shut down for usually just a second or so for it to get cleared. Sometimes it took longer for maintenance to bring the system back up. But it was just massive amounts of information, or I shouldn't say information, but data that they were collecting. And so data is great if it provides information, right? If you can wrangle that data and understand it, and sometimes it's summarizing it, sometimes it's watching for trends, sometimes it's making comparisons. And so that the whole idea is that it's the data itself is a starting point for us to create information. And we often use charts and graphs as a convenient way to convey data as a bit of information. But excuse me, the overall reason that we're doing it is that we or somebody else needs to make a decision. You know, are we achieving our uptime objectives? Where's the pain point that we need to make improvements? Is this product meeting its business objectives for warranty accruals and warranty returns? Is this the right vendor for this component? Is this process suitable for going into production? On and on and on and on. There are thousands of decisions that occur in most any engineering team on a regular basis that oftentimes relies on the data. And a big part of that is how well do we understand that data so that we can make the right decision, right? And sometimes we don't have enough data, right? We don't get enough samples, we just don't know. And then we create experiments or create measurement systems to go get information, go get the data and get the information so we can improve our decisions. What I find more often than not is that we have plenty of data, and then we have very crudely created charts and graphs that are to be the information we use, but in some cases they just further confuse what we're doing versus not. And so the importance is to get your graphics created well so that they are useful information for making decisions. All right, so let's dive into the deep end here with a quick question to you. I know you've seen graphics that are good, bad, and indifferent, and so on. What's some of the worst ones you've ever seen? Any quick examples or ideas or suggestions of what would make a bad graphic? And I'll throw out one of them is that it has no labels whatsoever. I was working as an expert witness a couple of years ago, and the Discovery provided all these great Weibull charts. At least I think they were Weibull plots. Um, but all the legends and axis labels and anything that was text on the graphic was blanked out, was redacted. So it really wasn't all that useful. That was a pretty bad graphic, but I think that was, I don't know why that was done that way, but hopefully when it was not redacted, it was useful for the people looking at it. All right. So any too many axes and variables. Yeah, it can, graphics can be very confusing. Good one. Good morning. Good morning, Julie and Chris Tomo. I'm sorry, I probably am not pronouncing that right, but welcome. Glad you can make it. Chris. Okay, thanks. All right. Well, I anticipated I'd get maybe a couple ideas here or not. And welcome, Christine and Krishna. Oh, good day, everybody. All right. So I always go back to the old, and I don't know whether they do it or not. I haven't seen a USA Today in a while. Using the wrong type of graph. That's a good one. Yeah. And one of the worst kinds of graphs is a pie chart. And in this particular example, it has all kinds of problems with it. Can you see a few of the things that are make it less effective than what really should be? Right? Click sense platformers, shape value, Pareto. Okay, I'll have to look into that one. So yeah, doing drop shadows, making them three-dimensional bar charts when the data's not on three axes, for example. Um, yeah, and this particular graphic has a drop shadow on the pie chart. I guess they're trying to make it look like a basketball of some sort. Um, the one that jumps out the most for me is I'm not sure if all of those 5 different things they have on the chart are comparable. They have 81 local newspapers, 81 local Gannett newspapers, and then next to it is 32 million fantasy sports consumers. Although is 81 individuals comparable to 32 million? I don't know how that works, how you compare those things, right? Exactly, Sean. Multicolor background, text is in areas is hard to read. They're putting things in a comparison mode, which probably really shouldn't be compared. But they also, a pie chart often is used, and I have another example that brings this out a little bit more. Yeah. And, they add all this. I know it's supposed to be of interest. This is about newspaper or basketball, but from what's in the data set, I have no idea if this is just a basketball thing or football or soccer or, why did they choose this realm of graphics? And the most dominant thing on the graphic is this big red rim that catches your eye right away, which has nothing to do with the information they're trying to portray. And so there's all kinds of wrong about this. No offense to Tom and Jim, who apparently created it or put it out there. Another one from back in that day when USA Today was doing these snapshots was this bar chart. But notice, and they did this a lot, they would put it at an angle. In this one, they're trying to convey that it's on the inside of a parachute, I think, and which makes it really hard to make comparisons. You would expect a bar chart to be proportional, right? And it roughly is. 28 and 29% are pretty close together, but is the 18 and the 34 twice as big or not? At least they put the percentages on the end of the bar charts. Sometimes they didn't even do that. They just showed the relative frequencies without the percentages. But they would cant it or make it some weird shape or build it into a graphic, making it really hard to understand it. Bar charts almost always are horizontal or vertical. which makes it much easier for your eye to make visual comparisons, to make comparisons over or magnitudes and so on. Pie charts in general are, in my opinion, the worst way to present data. It is very difficult to compare magnitude or volumes or areas in general, but it's even more difficult when it's in a pie shape, because while we can sense the relative difference in area in squares or in basic rectangles, pie shaped is not something that we're particularly good at. And at least here they're all listing things that are comparable, right? They're all pie flavors, but the ability to use this very scant amount of information in a meaningful way is muddled by being put into a pie chart. And then it just doesn't help. It's cute, right? Put it on a pie and a pie plane and a checkered cloth. Those are all fine. The other thing they did well here is they said where the data came from, a survey of 1,000 adults. Now, if you're going to dive deeper into this, you would need more information, more context, all those kinds of things. But they provided a bit better than that other pie chart, but it doesn't help you as a reader really understand what's going on here, right? So it's one last example. I guess I was looking for food examples when I was looking for these graphics. But here they took what could have been a really simple bar chart, and they tried to get cute by doing little chopped up cubes of onion and the colors of the various different ingredients and so on. One they don't have on here is salsa. I understand that salsa in general is overtaking ketchup as a condiment on hot dogs and most anything else. They didn't need to do the little cute stuff in drips and drops and so on to convey this. At least the hot dog and the mustard bottle are out of the way of the data. So this one's a little better than the others, but it's still not all that hot. And those are by far not the worst. Yeah. And at least it totals at 100. That doesn't always happen. That's true. All right. So what's effective? What makes an effective chart? All right. I should say most anything that doesn't come from Excel would be a start. Although it is possible to get good graphics out of Excel, but it does take some work, and I have an example of that. But first off, just keep it simple, right? It takes more work to make it simple and still convey the information, right? If I'm going to do a Pareto of issues that are facing our product, right? We have a number of different issues from our testing or from our initial product launch, and we want to create a Pareto chart of that. Now, let me do a quick drawing here and turn my phone off. Let's see, where's my line? I'll just use this. There we go. All right. Oops. So let's say I have, and I'm just trying to get a handle on my pen here. Sorry about the. And then if you do this, right, you make a really fat, wide one, and then you make another one, and so on. And then you do the other way out here, right? If I then label what each of these are, and then I add a text box that says, here's the title and the date, who created it, the committee members. And then we add a frequency line here that has a bunch of stuff. And then even better is if, well, that's hard to read if just tick marks on the side, so I run them all the way through. And you can see where I'm going with this, is that I can take what could be a very simple graphic and I could really clutter it up with all kinds of things that really don't help us. Right? So the basic idea here is to make it as simple as you can, right? there's no real reason to make a Pareto chart that has all of that extra stuff in it when it's really not needed. What is the minimum amount of information you need to make a legible, meaningful chart, right? And so it'd be the relative frequencies of the issues that you're facing. Keep them all the same size so there's not a discussion about why is this one really fat and why is that one, what's the difference in area and so on. And we go on through here. I don't even really need a line underneath it. I don't need a vertical line because I could just put the counts right on it, right? Oftentimes you don't even need that. All I'm really looking for is what's these top 2, 3, or 4 issues that I'm dealing with. And you may put a title on it saying this is from XYZ process or this is from product launch XYZ, so on. But I don't need horizontal lines. I don't need vertical lines. I don't need different colors. I certainly don't need it 3-dimensional. I don't need it with massive amounts of background and so on. Let the graphic tell the story in a context that's the absolute simplest you can get across. Because what we really want to know when we look at a chart like this, what are the number 2, 3, and 4, the top couple of issues? And are there related issues that maybe we could bundle together? And so the relative magnitudes ordered plus their titles is really about all we need. All the other stuff that whatever package you're using wants to add to this is really not necessary. Keep it as clean and as simple as you can, right? Mini tab, and it just is great for putting a great big gray border all around it, and you have all this axis and tick marks and all these other information that really is not necessary. So it's one thing to keep in mind as you take a look at creating graphics is just keep them simple. And I have some examples coming up that'll hopefully illustrate this to a little bit. The other part is keep it clear. That's where the examples of poor ones, they clutter it up with all kinds of background graphics or what is hopefully trying to create some eye candy to get you to look at the graphic. But then you look at the graphic and you're like, well, where's the data? How do I interpret this? What's important? What should I be paying attention to? Whereas with that basketball hoop one, is this about basketball contract of some sort, or is this about sports media stuff, or what was this graphic even about? And then it had all kinds of other problems with it. If you're going to create a graphic, some piece of information about some data, well, what is it? What are you trying to convey? Is there evidence of a change in a process? Is there evidence of a trend? And how do I best convey that trend? And so one of the tricks, and this is a devious trick, so use it cautiously, or don't use it at all, what I really should say. But let's say I have a graphic, and it's an XY plot, and I have time, right? Should always label your axis to some extent, so I have time, and pardon my hand, I'll just time. And let's say we have count on the vertical axis, number of units, 100%. Go like that. I really need to get a better pen. So if my graphic looks like this, what can I conclude from that? What does that really mean? Is there a trend? Is there a time series event occurring? Is it stable? Right? Is this something that, I see these kinds of plots all the time on like a quarterly basis or a monthly basis of giving a summary of some activity, like warranty returns, for example. But let's say the message here is that it's doubled, the failure rate is doubled over this time period from, say, January to July, right? A better way to convey that message that it's doubled because of the scale going from 0 to 100% flattens this curve right out. But remember, all my data is like in the 2, 3 5% range, right? So let me get rid of my chart. Another way to do that is make your scale. Let's say this is 10% now, not 100%. And now my curve looks more like that. One of the guidelines I've read about from years and years ago from a number of different authors on creating graphics is that if you have a trend, create the line or the trend element of your data and your curve such that it's about 45 degrees on the graphic. It is easier for a human to interpret than when it's flat or almost vertical. And so if this is 5% and this is 10% up here, we can see that it's gone from 5 to 10% very easily, as opposed to when it's flat and the 5 and 10% are very close together, or 10% are very close. Still doubled, but it looks like it's stable, and vice versa. If you make it very, very steep, and by shortening the time axis, vice versa. If you make it, then it's more aggressive than it really appears. But the way we interpret, especially trends, is best done when the trend is displayed and the scales are set so that it looks like about a 45 degrees. It allows us then to interpret the magnitude, the changes, the effect of what's being presented more readily. We can interpret it easier, right? And so if you are consistent in setting your scales that way, it really, really helps. Especially like in this case, that way, they want to convey that it's like in the failure rate over this time frame. This failure rate, that's the point or objective of the message. If I presented it on the full scale, point from 0 to 100, and it went from 5 to 10%, that gets lost. The graphic at first glance, like, oh, it's stable. And so that's what's the message that this graphic is trying to convey? And then engineer that graphic so that that message is clear and easy to interpret. Okay? And then one last step is let the data present or speak. One of the very first essays I wrote for the Ascendo site and for my blog was let the data sing. Let the underlying information in the data tell you the story, right? And so if I'm presented with a simple regression plot on an XY scale, and I left the scales off because it really doesn't matter what we're talking about. But let's say it's we're dealing with a repairable system, and this is the arrivals of repair requests for this particular piece of equipment. And if I create a time scale and I have the number of returns or number of repairs on the vertical axis, and I just give you a straight line plot like this, I'd have to look at the scales to see what's the magnitude and how much it's changing and all those things. And then you'd probably start thinking about, well, what's the cost of those repairs, the amount of downtime, other things like that, but which are all good. It gives us some information from the data that allows us to ask better questions, to dive into the data a little bit better. But the cautionary part here, along with being clear and clean about what we're presenting, is that sometimes the data itself the information gets lost if we over summarize it, if we over contort the data. Now, it's very easy to do a straight line linear regression. Just about any package, even a ruler on a piece of paper, does a good job at fitting data, right? Now, this all works just fine, right? If my data is reasonably along the straight line, right? Then there would be no argument. The data looks great, and the line represents that data set fairly well, right? Now, we would want to consider how much variation is considered too much and all those other things, but there would be very little argument that this straight line fitted line to this data is appropriate, right? In vast majority of cases. But let's say we were in a hurry. We didn't really plot the data versus the line. We just automatically threw the data in and created a regression, plotted this line. But if the data actually looks like this, right, that regression line is probably still the appropriate straight line to represent that curve. But obviously, if you would have plotted it with the data points, you would go, there's something else going on here. We need to investigate it. And so when it adds to the story, right, plot the data. And in the generation of your graphics, use the data plots. If they are distracting, get rid of them. If they tell you a different story that this line doesn't really fit, maybe use that as a comparison. This line is our expected performance, and here's what we're actually seeing. Now we've got a more interesting, more ability to tease out what this data is telling us. And so that's the main point there, is let the data tell the story and guide your creation, but also help you in telling the story of what the point is of that graphic. So some examples of great graphics. Now, I don't know that these are the ultimate greatest of all time, but they're ones that come to mind from the reading and background and research I've done. I don't know that this is one of the best of all time but it's using rectangles. It could have been presented a number of different ways, like stacked bar charts, which are really hard, like pie charts, to interpret. But it gives you a sense of the magnitude of the proposed versus imposed, right? It gives us, and those are comparable. There is $1 trillion of proposed tariffs recently, and I think this was from last year, and it might be more by now, but only a fraction, roughly a third of those have been imposed, right? Now, they didn't clutter this up with specific dates or with tallies or values on it. It was conveying the message of, well, not everything that's proposed is actually implemented. And it's the main point of this graphic. And I thought it presented it it includes a timeline and it includes magnitude. And it's really all that's needed to tell this story, right? So that's one example I came across. This one's a classic. It's an older, I think it was created in the mid-1800s, but a historian was looking at Napoleon's march to Moscow. There's a slew of information in here, which could be a very complicated graphic. But the width of the line, let me get my little pointer here. There's a number of different things. There's geography and routes taken. Where's my cursor? Here we go. But the width of this line, of this bar here, is the number of people, number of men or soldiers that started. And it's roughly 422,000 soldiers started this march, right? And a few split off. 22,000 went north. Another 33,000 took this little detour over here. The black lines are retreats. So Moscow, out of the 422,000, 100,000 reached Moscow. And then they were there for a little while and they started their retreat. These are temperatures. This is a temperature scale that's under here. It was cold, right? Every time they crossed a river, here's an example here that's telling, is they lost people. This one, they lost almost half of the remaining army there on one river crossing, right? There's another river crossing here. They lost a good number and so on. This march was brutal. In dead of winter going to Moscow, the folks in Moscow simply evacuated the city. There was nobody there for them to conquer or to control or do anything. They took all the food with them and they left. And that didn't help them much, but it has distances. It has some geography and paths. It has the magnitude of the soldiers that were remaining as they marched in and marched back out. It represents both temperatures and there's that were the impact of river crossings in particular on the well-being of these soldiers. It conveys a lot of complex information. I think there's 7 different dimensions in this, and it does it in a very simple graphic, right? Being in French doesn't help me at all, but I can still get this message. I still see the message once I understand that this is showing the size of the army at different points in time. Yeah, and it does, Elena, it does come from Tufte's book. That's where I first learned about it. And I saw Edward Tufte in a presentation in Palo Alto years ago, and he talked about this graphic and the simplicity of it for the complexity of information it provided is an example to strive for. Now here's I looked and looked and looked for a good histogram, right? Just a simple histogram. And most of the histograms I saw had great big heavy borders around them, heavy lines through the middle of it, three-dimensional graphics, all kinds of weird things to make it work. But this one provided labels, count and price. It also included a very light gray hash or a grid on the background that allows you to read it. It didn't need to label every single tick mark, which adds clutter to it. It added enough so it makes it easy to read. It also, they could have gone to every 50 in the count or every 50 on the price and added or every 25 or different scales and added more clutter to it. But they put just enough labeling in tick marks, axis labels, that you could read it. Now there's no outside box. Notice the grid lines just go off and end. They don't have a containing box. That's done by the space that it's inside of already. It's not a different color. This was actually transparent on the background. And it has a simple label of what it is. It's easy to interpret. I'm not sure I would want to stay in the very few that are like $25 a night, but they might be very nice, who knows? And all the way up to $300. It gives me the range. It gives me where most of them are. It provided the only thing that's really missing from this is, where is this? Is this Airbnb worldwide or is it in a particular city? And that might be contained in the context of where this graphic was presented. But it's very clean, right? And that's often all we need to clearly provide the information. Is we don't need a whole bunch of other information and over cluttering of the axes to bring the information across. So a couple things at least one example of a histogram I liked. All right, some of the basics. Somebody mentioned earlier is, use the right type of graphic. And here it's really the form follows the function, right? If I'm doing field returns or repair requests for a system, I could just put them in a great big table, and here's a bunch of data in a graphic form or in a spreadsheet, and we know that provides a way to contain or present the data, but it doesn't really provide a lot of information. It doesn't help us to know if there's a trend. Well, then a regression or a non-parametric plot that shows the trend would be appropriate. If the intent is to show that it's a stable process, well, then a control chart of some form or function may be the right way to do it. One of the things that I saw when I was looking for good or bad examples of all kinds of different charts is people will put drop shadows on it, and they put three-dimensional bar charts. And even though the data is not in 3 dimensions, they make them volumes instead, or they cant it or make it on an angle, as the folks at USA Today did that all the time. So, and Matt, I see your question on the, why avoid pie charts? They are visually exceedingly difficult for people to interpret and make comparisons. If I wanted like that apple pie chart, Apple was 27%, but were, peach and cherry about equivalent between the two of them? Or, were they 25%? I think they were 12 and 13. or something like that. But it doesn't come across, you have to do the math to make comparisons on a pie chart, right? It also takes a lot of space for what essentially oftentimes is a very small amount of information. Use a bar chart. It is much cleaner, easier to interpret than using a pie chart. My biggest complaint with pie charts is making comparisons is you have to go to the math to do it. It's very hard to do well visually because of the shapes. And rectangles are much easier to interpret than triangles, rounded triangles. So if we're presenting field data for, say, field returns for a product and it's time to first failure, right? Or just total failure of the system and it has to be replaced, it's not a repairable system, then a Weibull plot or a log normal plot. But then which one do you use? Do you use the probability density function, or do you use the cumulative density function, or hazard rate? How do I present it? Well, what story do you want to tell? Right? What's the relevance of what I'm trying to convey from that data? So let the specific graphic come from what's the objective of that graphic. Now, one of the, and I know I've talked about it in the presentations before, is when you get a pile of data, just plot it. Plot it a dozen different ways. Do a histogram, do a fitted curve to it, try it in a cumulative distribution function, do a dot chart. Well, how can we tease out where's the information in this data? What is it that's in this stack of information that we want to convey to somebody else? Now, sometimes it's a standard format that allows us to do comparisons. Well, one of the things is the typographic then should have that comparison overlay versus having them on two different pages or two different slides, for example. So like on this graphic in my little image here, he's pointing at a green line and a red line that are bouncing along comparing to each other. Now, I don't know what the context is of that particular image, but it allows us to do a comparison. Was it this year over last year, or was it whatever the context of that message is? But if it's a comparison, make it easy for somebody. Now, the upper part of this blue, red, and yellow stacked bar charts, those are a lot harder to interpret. You know, if you're looking at just the red segments of it, you can see some are bigger and smaller than other ones. But is there a trend? Is there a pattern? They're bouncing all over the place, but that's because the lower stack of that bar is also changing. So it makes it very difficult. If it's the total magnitude that we're looking for, and this conveys what makes that up, that's a different story than if we're looking for how does the red change over time, for example, just one part of that. So it's get the data, look at it a number of different ways, and what's the story that data tells that provides the information necessary for the decisions, going back to the start of this thing. What's suitable to convey the information in the data set? And sometimes it's more than one graphic to make it work. Axes and scales. I'm as guilty as anybody else at not adding appropriate axes. And using my pen on this stylus I'm using makes my handwriting even worse. So it's not that it's great to start with, but label the axes, right? Make it clear. That one example of the histogram showed a very nice way to do it. Add just enough labels and at the appropriate scale so that it's easy to interpret, not cluttered. And this gets a little bit into the artistic side of things, but make it clean. Just enough information to review, but that's about it. Relative amounts, Carl, it's a good question. Bar charts is often the simplest way, right? If you're also looking at a graphic that's relative amounts, but it's, say, a distribution, if it's just two numbers, one's 20%, one's 40%, put them next to each other, right, on a bar chart. If I had two circles next to each other, our ability to interpret the area of a circle makes us think of 2 pi r and start doing math in our heads to figure out which is bigger than the other. especially if they're close. A bar chart on an appropriate scale conveys the magnitude of that difference, if that's what's important, or the relative similarity on a scale, if that's what the message is, right? You can change the scales to with the same data to tell either story. So part of realizing when you look at a graphic, it's part of what the graphic creator's message was and what was their context for making that. And then make the grids, if necessary, light and be visually more subdued so that the data parts or the information parts, the bar charts, for example, stand out. That's what we want to look at. And then we use the other markers for information as secondary. And Tufte has great examples of in his book of really bad scales and graphics and all those kinds of things. Labels and legends provide context, right? You don't need to do the thesis. If it's an infographic, then it's a different objective, right? You're telling a story through multiple graphics. But if you're putting up a graphic, and I've seen these in technical presentations all the time, they put up a beautiful cumulative distribution function of, say, some field data that they're collecting and analyzing and comparing different vendors, for example. They have all these two lines on there. And then they add a bunch of text boxes and heavy graphics and the great big legend that says this was done by this team on this date, and here's the considerations, and here's the fitted curves, and here's all the assumptions, and it's a mini thesis all in one graphic, right? There's a place for all the context and discussion, but just because you're going to put it up on a PowerPoint slide doesn't mean you put it all on one slide, right? Let the information in the data convey the story, and then the details and context and presentation about it help you to get rid of that, avoid the clutter, only add what's necessary and to convey the information. All right, so I'm going to just ask a quick question, and I know that I've jumped on Excel earlier, but I'm making the assumption that a lot of people use Excel. So how do you make a histogram? What tool would you use to do a histogram? Minitab, Jump? Any R out there? Sean, Excel? I'm sorry to hear that. But we all have it, right? It works. Yeah, okay. Power by or BL. I'm not sure what that one is. Interesting. Lots of Excels. Anybody using MATLAB or Mathematica or R or S? I think S plus is still out there in some places. Looks like Minitab's going to win the day here. It is easy to use. You put the data in, push a button, histogram, right? It's way easier than Excel in general. All right, cool. Well, here's a little bit of here's some data. Okay, I found a data set and an example, and I got a couple of graphics from it. And they had 40 students, and they were going to give test scores, right? And it might be customer satisfaction with our product. It could be whatever it is, but we have 40 pieces of data. The scores are from 0 to 100 out of 100 points on this exam. And the values range from 36 to 100. I think the highest test score in the data set was actually 99. So, but they typically, the lowest score was 36, and it goes up to 100. And so what we did is we just took that stack of scores. It's a one-dimensional set, right? It's just a vector of data. And we put it in Excel. And this is using Excel 2016, I think it is. And we just hit histogram. Okay? Make this chart. And so it has to make a bunch of decisions about, well, what's the bin size, right? And how do we break the bins into equal segments or whatever? And so it decided to use them. I think they're in groups of, let's see, what is that, 15 roughly? No, 22. It's some strange number. I'd have to, it's 18, I think it is, if I look at it closer, 18, right? Yeah, and Carl, you're exactly right. There's great information about how to do this stuff and get it out there. But 18 is not an easy number to break up, right, in your head. You're like, okay, Is this what this means? Is this it? And then whenever I see a graphic, whether it's a histogram or anything else, is this, I call it a sniff test. And does this look right? Well, the first thing that jumps out is we got this 108 in the last bin. It goes from 90 to 108. Well, the top score is only 100. So how many people got extra credit? Is that part of, there wasn't anything above 100. Why does this graphic go out to 108? That conveys some information that's not relevant to that data set, right? There's not labels on it. It's a very simple data set. It's got a default for where the title is going to go, which is okay. The grid lines are subdued. This is actually not bad, but do we need a label on every 2? Could we have done every 4 or every 5 or something like that? And then the bins being, we can control that. And it takes a little bit more work with Excel, but you can set bin size, or you can set quantity per bin or something like that. There's a couple of settings you can use. And you can change the bins. All I did here is change the bins to be, I think it's every 9, maybe it's 10, 9, right? 81 to 90, and so on. Yeah, 9. And I get this much stranger looking graphic, right? Much different information than what this one gave us, right? This one looked like, it could have been a normal distribution in our class. But when you break the bins down from 18 to 9, you just cut them in half, we get a completely different picture of what's going on with the students on this particular exam, right? Exactly, Sean, is play with the bin size, play with your graphics, whatever they are, until it has either a question in the data that tells that there's something going on here. There's a separation in your class, right? There's some really good students on that exam and some really poor students on that exam, and a significant proportion. And then a cluster in the middle. Another set, and this one was using bins of 10. The last one was a different size, which is also not often recommended. This one went from 35 to 50, and then 50, 60, so on, 90 to 100. It gives, again, a different pattern than the previous one. So bin size is one way that you can really view your data in a number of different ways. Keeping it simple is keeping them in regular cadences so that they're easy to interpret. Keeping them equal bin sizes is a piece of that if that's one of your messages. There's a number of different ways to construct these things, but you can see it's the same exact data in 3 different plots, and we get 3 completely different ways to do it, right? Yeah, and JUMP is a pretty powerful package, Charles, and so they do a pretty decent realm, right? Yeah, and you want to keep the data, the scales of your stuff within the range of the data set that you're using and so on. And then there's all kinds of smoothing and leveling and all kinds of criteria for what's the appropriate bin size. I find whether it's setting scales on a regression analysis or looking at a projection for future failures, or setting the scales on a mean cumulative function or a histogram or any of these, is that it takes some experience in practice and try it a number of different ways so that it conveys the message that is really coming out from the data. What is it you're trying to say or to use the data for, right? This frequency plot on the right, if the scales were A, B, C, D versus the percentiles, or 90 and above is an A, 80 above is a B, and so on, then that would serve that purpose. Here's how many students got a C, for example, or a B or an A. But it's, what's the purpose of creating this graphic? What am I trying to convey? What's the objective? I think you've heard that a few times so far. All right, here's some real data from, and these are mean cumulative functions. So what's this mean? How would you interpret this? This is a system. It's about a year's worth of data. The time is in hours because the system had an hour meter essentially on it, and we're using that as the scale. It was relevant for us. So what does this graphic mean to you? And this is, if you're not familiar with the mean cumulative function plot, it's the vertical axis, just the count of failures. Each dot represents a repair action where the system was down and we sent technicians out to fix it. and hours is just time. And this particular system runs between 18 and 20 hours per day, 365 days a year. So what questions do you have from this data? Yeah, Christine, that part where it goes steady, right? And you're talking about a high failure rate initially, right? It's going almost vertical, essentially. It's climbing pretty quickly. And then this part from here to here is flattening out, right? Almost to here. And then it starts creeping back up again and starting going more vertical. So I had the same question is, well, what's going on here? What happened such that we had, 500 hours or almost 1,000 hours with no failure, where before it was failing almost on cadence, every 300-400 hours, or every couple hundred hours we had a failure, or maybe two in quick succession, like here and here. So, well, I dug into it some more, and I found out that between here and this next point, the system was down. It wasn't running at all. And the same here. They were waiting for a part. The system was down for 1,000 hours. So what initially translated as it was running fine, which is the common interpretation of these kinds of plots, because the assumption is, when you use it, is that repairs are pretty quick relative to the time frame that you're showing. Well, here I had these big chunks where it was just down. And so it doesn't tell the story of, and so we had these long downtime segments that in this graphic then make it appear like it was running fairly well. Well, that's a problem, right? So one idea here was to draw or to add to the graphic a segment that basically said it was down for this period of time, right? That was downtime. This one is downtime. And do something like that to help convey that extra piece of information that's missing from this first plot. But my first question was, why did it go stable? And the answer was not that it was running, that whoever repaired it just prior to those big gaps did a great job and it was running. No, it was down, it was broken and waiting parts, right? Yeah, so the other part here is where it grows up like this. What's going on? Is this thing really wearing out, or is the repair actually working? And I think I have another chart that does a little better job of showing this. Right, this one. My first reaction to this one was, oh, geez, I got all these downtime again. No, this one was actually running the whole time. We would get two repairs. There's all these little steps in the data set where there were two calls, 100 or 200 hours apart, and then it would run for 1,000 hours just fine. And it's like, what's going on here? And then it started to get worse. What happened is at 6,000 hours, about halfway through this year, a new technician was assigned to the equipment, right? They're using similar processes to diagnose and repair the system. And usually this first one was, we reset the unit and it ran, right? But then it generally within a day or two, it was back again. And then that technician said, I was just here a couple of days ago or a few hours ago. Let me do another level of diagnosis. And then they would find a faulty sensor, or they'd find a dirty element, or they'd find a worn gear, and they'd do the repair. And then it would run great for 1,000 hours, right? It'd run fine for quite a while. The new technician came in, but didn't have that sense of this machine. So they reset, finally said, oh, there really is something going on here. It ran well for a while, reset, And then they got busy with other equipment and reset, reset, reset. And they got caught in resetting it and walking away because they were doing that on so many pieces of equipment that they didn't have the time in the day to do the diagnosis. And so, yeah, and these were single units that I'm plotting here. Now you can use these plots with the whole fleet and plot them all on top of each other. But when I plotted that initially, it was so confusing and so hard to interpret, it didn't tell a story, right? It didn't help us understand what was going on. So we chose not to use those. And here's another one that was in a mean cumulative plot that this one was actually running all the time. All the repairs were fairly quick, and it was running very, very well. The end of the story on this one is for the team that was working on it. They said, "Oh, this is a new unit, and it's got light loads, and it's in a protected environment where those other systems that show all the repairs are open to the elements. They're old units. We can't get spare parts anymore, and heavily trafficked, and lots of load." And so they had all kinds of reasons for the differences. Now, if I really wanted this, and I did do this when I was actually working with this data, I'd show this plot versus the other one on the same scale or on the same graphic to show that there's a wide range of difference in these things. Yeah, and these are, the time on these is running hours. This machine is operating hours. Because some machines, some of the systems in their fleet ran, oh, and and that's a good point. I hadn't thought of that before, is that some machines didn't run as much as the other ones. So this might have been a full year for this piece of equipment, where others were running almost 24/7 would be further out on the scale. So I probably should have rethought that and put it on calendar time. Yeah, that's a good question. There's always a way to make a graphic better. All right. So wrapping up here is that, take a look at your graphics. Take a look at the ones that you do on a regular basis, weekly or monthly or quarterly. Take a look at the ones that are part of an investigation, a failure analysis, or just checking your experimental results or your field data results or your production or repair rates for systems and equipment. What is it you're trying to do? Make a comparison, detect a change. Uh, the nature of that graphic almost always, and I suggest always, goes back to, well, what's the purpose? What's that underlying decision, and what information will help inform that decision so they make a good so that we make a better decision in general. All right, keep it simple, keep it clear, keep them elegant, which is not easy to do. It takes some work to do that. And then let your data tell the story, right? Let's explore what we're doing with the data we have, and let's not contort it to what we want, but let's let the data tell that story and be supported by the data, which is what we're really trying to do in the first place with all these graphics and images and analysis of the data sets that we have. So that's today's presentation. Let me I think I've got a conclusion slide here where you can still find the downloads, and the graphics are all still here. All right. And let me take a look if there's any questions, and I'll stay on the line. I know we're up against our timeline, but I'll stay with that. Yeah, you're exactly right. They don't show the suspensions, and the assumption with the mean cumulative plot is that the downtime is relatively short. And if that's not true, then it's not exactly the right graphic. You have to come up with some other way to convey that information. Yeah. And each dot, you're exactly right, Daniela, is each dot was a repair request. And sometimes it was just a reset, and they did basic safety diagnostic, and it was up and running. And other times it was, oh, there's a jam or a broken piece of equipment or failed motor or whatever. And some of those repairs were pretty quick. But on occasion, some of those repairs would take months, and that gets lost in this data set. Yeah. Yeah, Charles, I tend to stay away from log scale unless it really helps to tell the story, right? Sometimes when you have that big of a difference in elements on your graph, log is the only appropriate way to go. But make sure it's clear that you're on a log scale, like a mean or a Weibull plot. Well, it's